Our second to last presentation will be on beneficial silicon use in containerized crop production by Jonathan Frantz.
Thank you very much, and I really appreciate the offer to come and speak. I'm not alone in this. I'm going to be sharing data from a number of these folks, and a lot of them are in the room today. So I say container production, not pot production. And in the U.S., it's mostly ornamentals that we're talking about. 90% of all the greenhouse space in the U.S. is devoted to ornamental production, not a whole lot in food. The ornamentals are worth just north of $5 billion US dollars annually, and it's split evenly between woody ornamentals and herbaceous ornamentals. Highly controlled systems, though. A lot of these are containers, greenhouses, or nurseries, all in pots, and they tend to have an engineering system to deal with every problem. But even in containers, historically, soils matter. For a long time, we were just gathering the soil and putting it in pots and selling the containers that way. And as we saw before, generally the more acidic, weathered soils, they have less silicon. And so when you talk to growers, this is from a grower that passed away a couple years ago, but he had this great quote: "Soilless media is great if you have the right amount of soil in it." So not really soilless at all in that sense, but it points to some of the perception, I think, that maybe we've missed out. As we've shifted away from soils, we've accidentally gone away from silicon, and maybe we're missing some of those accidentally and missing some of those benefits. So when you look at a map of the U.S., you get a lot of different kinds of soils. And that big area in the middle, the dark green, those are areas that are fresh, young soils and have traditionally a lot more silicon, whereas in the red zones, you have less silicon. The reason I show this is because in certain areas, Michigan and Ohio, as well as California, and this region in Oregon, that's where the greenhouse and nursery industry has historically been concentrated. And in those regions, you see how patchy it is. So your neighbor may have quite different soils than you have. And so an individual grower may have had silicon benefits while his neighbor did not. Okay? Not much nursery and greenhouse production in the center, or there's quite a bit in the southeast, but that's where it's deficient. So were we seeing silicon effects all along, but we just didn't notice. Now, in the last 30 years, we've gone away from using soil in containers. We've incorporated more peat, sphagnum peat. And we've simultaneously gone to cleaner and cleaner water sources. We even recycle it, so there's no chance of getting silicon from weathered soils. We collect rainwater, so there's really low amounts of silicon in that. So there's a challenge and an opportunity in this system to incorporate silicon. As I mentioned earlier, here's another challenge. This is a retail area, but the production area looks much the same. You might have 30 different species on a single bench. So how are you going to identify what can and can't benefit from silicon if there is such a distinction? And within each of those species, you might have 1,000 different cultivars on the market at one time. So literally, they're growing germplasm from 30 to 40,000 backgrounds at one time. So it's a real challenge to come up with unique controlled systems for each of those species. And so they just don't do it. This is a quote that I think captures a lot of why silicon is unique, as well as why growers don't always embrace the opportunity for having silicon. It's evident only in adverse situations. So from a testing standpoint, you have to create those adverse situations, and so you pair a species with a stress, then you move on to the next species in stress, and you move on to the next, and it's difficult to just get everything, to test everything. Growers want to know if it works in their crop. It's great to show it in rice, great to show it in cucumber or soybean, but does it work in their crop? If they're growing 30,000 crops, that's hard to address all of those crops. We've convinced ourselves in these highly mechanized systems, these are hanging baskets inside of a greenhouse, highly mechanized systems, we can control everything. So maybe we don't have the adverse situations. We've invested all of this money in the control systems for heating and lighting and irrigation that we've convinced ourselves that we don't have these adverse situations until you do. This is a scene of nothing but poinsettias. They had 150 acres of these. I don't know what that is in hectares, sorry. But nothing but poinsettias as far as the eye could see. Whole racks of lighting that moved back and forth, an acre of lighting that moved back and forth. Highly mechanized, and so do we really have the adverse situations? Yes, we do, but we've convinced ourselves that in the greenhouse system that maybe we don't. Okay, so what are the challenges? Why hasn't silicon been embraced? We have unique environments, so there's an opportunity. System failure does happen, so it's not all the time, but when it happens, it's traumatic. Specialized production and post-production needs. So it's not just yield, it's growing beauty. It's growing lasting products that are grown year after year and maybe have decades of production that you need to worry about. The challenges to this, though, are thousands of species are grown at once. You infrequently have culture specialization. How will they respond? Are you just throwing money away if you apply the material to those crops? That's what the growers want to know. And how do you integrate supplying silicon? So what form of silicon? There's another question earlier. What's the best way of supplying silicon? That's what the growers want to know as well. So there's the challenges. Well, that guided us into how do we start our program with ornamentals. And so we evaluated, 40 or 50 different crops and divided them up into high and low. And our numbers were different. Our threshold was different from a lot of folks. We had 0.1% dry weight. We evaluated them in a hydroponic system. So we had lower thresholds. But you can see about half were in the high and about half were in the low. Okay, so this guided our thinking into only focusing on those high accumulators. And we focused on zinnia, all right? So what does it do? That's what the growers want to know. What does it do? And we looked at a number of stresses that are common in greenhouse systems. Powdery mildew, copper toxicity, and what's less common is drought. So this was our model plant. Zinnia, it's a high accumulator. It accumulates about 1.5 to 2% silicon when you supply it sufficiently. Powdery mildew, on the sake of time, materials and methods, we grew plants and we measured stuff. With the powdery mildew, we had very controlled chambers, controlled inoculation, and we monitored the spread of the disease on the leaves. You can see on the right side is a plant that was grown with silicon, and the other plant was without silicon. So you can clearly see, and this has been shown lots and lots of times, that the plants with silicon don't have as much powdery mildew. And I emphasize as much because growers are really looking for that magic bullet. They can control this easily with a pesticide or with a fungicide. But we need to emphasize that this isn't going to cure everything. It's just enhancing the ability for the plant to fight the pathogen itself. Here's just another picture of zinnia. We've done this as well with phlox and rudbeckia and verbena and cucumber. And all of those crops are interesting not only because they're dicots and they're accumulators, but they all get the same powdery mildew species. Making me wonder, was there some kind of evolutionary or co-evolutionary response where these plants differentiated so that they could use silicon in fighting this one pathogen? So we moved on to copper, and metal toxicity has been studied a lot. In greenhouses, it's important because we use a lot of copper in fungicides and controlling algae and things like that. And levels as low as 10 micromolar, so less than 1 ppm, it's sufficient to cause damage. And when you look at the rates that we recommend people applying to plants to control these pests, you're talking about hundreds of parts per million or thousands of parts per million. So there's real potential there to get copper toxicity and copper damage in greenhouses. And thank goodness we can't get a whole lot through the leaves, or else we would have a whole lot more copper toxicity. So that's why we looked at copper. Again, we grew plants, we measured stuff. We grew these hydroponically. Half received about almost 2 millimolar silicon, and the other half was just a trace amount. After 2 weeks, we imposed the copper toxicity, and we saw the results. Okay, we also measured silicon content, copper content. We measured some enzymatic stress assays. I'm not going to show those. I'm going to come back to them in a different set of data. This is the dry weight. The top, middle, and bottom are leaves, stems, and roots. The dark bars are the controls, so without silicon, and the light gray bars are with silicon. And you can see the stair step as you go higher and higher with copper. the size of the plant gets smaller and smaller. With silicon, the mass doesn't change. So it's clearly benefiting the plant through a greater mass. It's just alleviating the toxicity. When you look at the copper concentration inside the plant, we see with higher silicon, you get lower copper concentrations. So that was good, but with Arabidopsis, we didn't see that. So that's pretty interesting to us because it suggests potentially some different mechanisms in different plants. With Zinnia, we see a suppression in uptake. With Arabidopsis, we do not. We pursued this with Arabidopsis, and indeed there are some metal transporters that are differentially regulated with and without silicon. What's been shown before are the COPT1 and HMA5. These are copper transporters that are induced with copper stress. But when you add silicon, their expression goes down. So there's something mechanistically going on there, and maybe this isn't the same effect that you get in the Zinnia plants. The molecular tools are not available for Zinnia, so we can't look at that right now. Drought. This is kind of a new area. Drought in a greenhouse is when a system fails. They use the same amount of water, so the water use efficiency was enhanced. Didn't see the effect with deficit irrigation, so we were only irrigating them with 1/3 the total. So this was great. We repeated the study, more reps, did a better job on everything, and we didn't see the effect. So that was a real puzzler. And the next couple of slides I want to show you are with my collaborator, my former advisor, Bruce Bugbee at Utah State. He's doing drought studies with corn and with wheat and with soybean. In every one of these cases, you clearly see an effect of silicon enhancing. And we cherry-picked these data to show the best results. And that's a challenge with these kinds of studies. You don't always get the effect, and that's potentially one of the reasons why we're not seeing people embrace silicon as fast. It's user error, as he used to remind me all the time of what I was doing in the lab. So we're still trying to evaluate how do you induce these stresses in such a way that you can get consistent results. That said, the results we do get always tend to be positive. We never see a negative effect with drought, but it's not always statistically significant, and that's a real challenge. Okay, different kind of system, but still dealing with drought. This is post-harvest. Neil Matson did this at Cornell, where he grew poinsettias with and without silicon, then put them in a classroom to simulate post-harvest or on your mantle or your dinner table after you buy a poinsettia around Christmas time, and didn't water them. That's what people normally do. And without silicon, they started to wilt faster, much faster. In fact, about 3 or 4 days faster than plants with silicon. He continued to let them wilt until they were very sad-looking plants at the top and rewatered them, and the ones with silicon recovered faster. So this was, that grower that I showed with 100+ acres of poinsettia, this was the light bulb moment for him. So they're very, very interested in this work. Different kinds of data, different crop, tobacco, looking at virus infection. And for any graduate students in here, boy, if you can do one study, publish one paper, and you've tripled the amount of data out there on the effect, you've now become the world expert in virus response with silicon. We saw this effect with tobacco, more silicon, you reduce the disease progression. And then again, with stress, you enhance silicon uptake. So you're inducing silicon uptake with stress. We've now seen this in probably 4 or 5 different crops with slightly different stresses, so it's not unique to virus, and it's not unique to tobacco, leading them to coin the CISA, the stress-induced silicon acquisition. So it's a phenomenon that we're going to continue to study. Perhaps most excitingly, sticking with tobacco, they've found a possible silicon transporter. It's a protein, a membrane protein that is responsive to silicon addition. It downregulates, and it has a lot of the characteristics of silicon transporters. So why is this so exciting? Tobacco, poinsettia, those are plants that aren't accumulators. So these are non-accumulating plants that we've tended to ignore historically, and yet they're responsive to silicon, and it opens the door for not just significant accumulators, but every plant to be responsive in some way to silicon. So when we look back at this list of plants that we've evaluated, I now highlighted in yellow plants that have responded positively or minimally to additional silicon. And you can see quite a few now in that low group that are responding to silicon. So maybe this whole idea of high accumulators, low accumulators, yeah, you can classify them, but does it matter? I'm not sure if it does anymore. Okay, so my work tends to be very applied. The growers want to know, all right, great, you prove this all, but if it's not practical, if it doesn't make sense to apply it, what are we going to do? Fortunately, there's a lot of solutions out there to this problem. There's a lot of products that supply silicon in different forms. I'm not sponsored by Protect, but I had the bottle handy, so I scanned it. And it's one of the many products out there that can supply it. I'm going to highlight that right now, but I'm going to go through each of these. And I say something wrong here. I say it cannot be mixed in the same stock. You totally can mix Protect in your stock tank. It becomes difficult, though, because at high concentrations, and when you add it to your mix, you have to mix it very quickly, or else that little microclimate is very high concentration. So it's just a challenge, but it's a great source of silicon. And there's a few of these soluble silicon forms that are generally potassium or calcium or sodium silicate. For a grower, they don't want to mess with mixing fast and having separate injectors and all that. So this, as a sole solution, was not as attractive to them as maybe some other things could have been. All right, so back to this. Looking at carbon-based forms of silicon application, miscanthus, rice hull. We're also looking at composted material for the organic group. And it's funny listening to the organic community because they swear it's all in the soils. It's what I add, and that's the benefit. It's magic. It's a black box of something that they don't understand, and I'm wondering how much of it is the silicon that they're accidentally adding to it by way of these different feedstocks. So we've looked at this, and yes, indeed, you can get silicon delivered to the plant. So depending on your preference for adding a liquid or a solid, you can get quite high amounts of silicon depending on what you choose. Does it work? You can evaluate powdery mildew, and yes, you get more without these additions of silicon. It's kind of hard to tell what those numbers mean, so I took pictures. And the peat and pine bark on the left, see a lot of these colonies of powdery mildew. A couple here, but it's suppressed. 1 week later, looks like it snowed in the greenhouse, and the other one, just a couple of colonies still. So that was exciting for the growers. But this last thing, I'll spend a little bit more time on the slag. I didn't know a whole lot about slag up until a few years ago. For the sake of people who may not know about slags are non-metallic secondary products of steel processing, iron processing. They differ. There's a lot of different flavors of slag, depending on the furnace type. The furnace type influences what you can add to it to process it. But as a result, you have different amounts of silicon in the slags and different ability of the slag to change pH and different amounts of total silicon in the slag. So we're looking at a lot of different slag types and what does it do for plants. So this is a table that we looked at a lot of different sources of silicon. We had the control, fertigation, so that's that solution of silicon, 2 different forms of carbon-based silicon, and then at the bottom, 5 different classes of slag. In the middle, you see the amount of silicon in zinnia leaves. So it ranged from very low in our control plants up to 1.5% to 2% silicon. Looking at this range of types of slag, you can have sufficient or insufficient. So it really depends on the kind of slag that you have. Over here in the comments, this was more for growers. You can substitute lime for some of these slags, as has been shown lots of times, but the growers were really excited about that because they use lime already. And if the product is priced competitively with lime, it's an easy switch. They already have the equipment, they already have the machines to add lime, so then it's just a one-to-one replacement. Willostenite, yeah. So cost, depending on your system, it can be quite high. It can be no cost at all. And so this was the light bulb moment for a lot of other growers, because they realized not only can all my low accumulating plants potentially benefit from this, but I already have the equipment to add it. Looking back on our list of pros and cons, this thousands of species grown at once, not an issue. They know how to do this, and if you can apply silicon to everything, you don't have to target your mixes for the different crops. It's not an issue anymore. So will low and non-accumulators respond? Absolutely. I don't know if all of them do, but there's more evidence that it's a positive thing for all plants than a negative. There's a lot of options now. 5 years ago, there weren't these options. So depending on the grower preference for their carbon or slag or liquid or whatever, they've got options and they can incorporate it. So what's the state of the industry now? And this changed 3 weeks ago. I was ready to just gloom and doom, but 3 weeks ago, a lot of things happened, and it's very, very positive. Gradual acceptance of silicon. I now can talk to growers about silicon, and they don't say, what is silicon? They know about it, and it's generally positive. They want to know the details about it, so that's great. I call it the BASF approach, and I don't know if there's representatives from BASF here, but I like the slogan. It doesn't make the plant, it makes the plant better. So it allows the plant to do more things that it does in the wild. So they need to see that they're only going to see an effect in stress. It's a safety net for them. And you think, all right, we've added peat for water holding and air. We've added limestone for pH. We've added control release fertilizer for fertility. Now we're adding microbes, and now we're adding silicon. And what we've done is we've made reagent grade soil. So we've gone full circle. We're now using soil. We just built it ourselves. So with that, thank you. A lot of this information, the papers that we have are all on our webpage. If you don't want to read the whole papers, we've condensed them down to single pages to just take the important parts home. So thank you again for your attention, and if I have any time for questions, I'll be glad to take them.